Okay. We're going to use this equation, which is a lot like the last one, except we got this 4xy in here, which would occur if we rotated our coordinate system. Our constraint, going to change that a little bit too. It's not going to be the unit circle. We're going to make an ellipse out of it. 2x squared plus y squared equals 1. So we've got this surface up here. It's still a paraboloid, elliptical paraboloid, but rotated from the last one. And now we're looking at the values of that function, which would be the z-coordinates on this paraboloid above the ellipse 2x squared plus y squared equals 1. Okay? And that ellipse is, compressed in the x direction and, remains kind of the same in the y direction. Okay. Del F, del G, both easily calculated, so I'm not going to read it to you. Now, our condition is that del F is parallel to del G. Now, a lot of times people just cut to the chase and write down these equations. I think that's not a good idea. The reason I think it's not a good idea is you're skipping the meaning of the equations. And it's the meaning of the equations that will cause in the process of thinking through some unfamiliar problem or situation will cause you to all of a sudden say, okay, that looks a lot like the equation we get for Lagrange multipliers or something now, or this looks a lot like the geometry associated with the Lagrange multipliers. Can we adapt it to this? If all you do is skip to the equations, you'll never develop the insight that allows you to actually use this in a deeper manner. I said that better in class, but you can't always duplicate things later in the afternoon. Okay, so del F is parallel to del G. We want to write that down to remind ourselves of what we're doing. And then we write out that equation. And then we write this out. Okay? Or, at first I'd really recommend you don't skip steps. You write everything out. Number one, to make sure you do it right. Number two, to reinforce the geometry and the overall situation. At some point you can maybe just think through this and this, because it's pretty easy to think it through once you've got these gradients. But you should always be invoking this, the geometrical meaning of this, as you're writing it down. Okay? Okay, anyhow, you write down these equations then. Hopefully you write this down first. And then, you could write the constraint down, but you might remind yourself. You write, okay, xy is on the curve, meaning that 2x squared plus y squared is 1. It reminds you of what you're doing. And I don't recommend that you work these, especially when you're first encountering them, without continually reminding yourself of what you're doing and why you're doing it. Having written these three equations down, you got three simultaneous equations for x, y, and lambda. Okay, now I suggest that you solve these equations because we don't have time to do it, and I kind of want you to do it yourself anyway. We solve these equations by eliminating x and y from the three equations to get an equation in just lambda. Okay? So for example, I could solve this equation for y, plug that expression in here, and I just have now an expression for x and lambda. Okay? Then solve that equation for x, plug the result I get for y and the result I get for x in here, and solve for lambda. Okay? So, one way or another, eliminate everything but lambda and solve for lambda. Now you could also eliminate lambda and y and solve for x. That's perfectly permissible. The one thing you can't do is solve this by reducing a matrix, because these are not linear equations. Okay? These are. This isn't. And these aren't even linear because you have lambda x and lambda y here. They're not linear in the three variables. So none of them are linear in the three variables. You can't use methods of solving linear simultaneous equations. Okay.